Just wait. Huh?
Yes, sir.
Yes, sir.
Okay, you can start, Mantri sir.
Yes, sir. Thank you.
Okay.
Good
Mantri sir.
afternoon, ladies and gentlemen. Welcome to 9th series national level webinar, which is organizing by Sarat Chandra Pawar College of Pharmacy, Mathur, Pune, which is located in the Maharashtra. So today, a speaker is very dynamic person, Dr. Ashwin Kuchekar sir. First of all, I would like to thank sir for accepting our invitation and welcome you, sir.
Thank you.
Dr. Ashwin Kuchekar sir is the associate professor at Dr. Biswanath Karad, MIT, World Peace University School of Pharmacy, Pune. Today's topic is response surface methodology software in Minitab. It is such a wonderful and such an interesting topic for all of us in the research methodology. What type of the software and what type of the methodology, what type of the apps we can use to develop our methodologies, to develop our the research. And as you know, in all eight webinar, we are keeping the questionnaire session, and today also we'll give some chance to all the participants to ask your question. Indirectly you can communicate with our speakers today. So once again, I'm saying to all the participants, those who are interested to communicate with our speakers, kindly raise your hand. You can use the Zoom apps. In the reaction you can send, you can see the hand option and just raise your hand, so that it will be easy for me to announce your name after delivering speech of the speaker, sir. At the end of the session, I will announce some next upcoming event. That is, after the questionnaire sessions, I will say you what is the upcoming webinar tomorrow and day after tomorrow. That means 10th series and 11th series of the national webinar. So I will not take your more time. We'll start the session very soon. Now I hand over to Dr. Ganesh Dama sir, Principal of Sarat Chandra Pawar College of Pharmacy, to take the in charge and start the welcome speech of our Dr. Ashwini Kuchekar sir. Sir, it's
a very good afternoon, sir, to all of you. I think that I'm audible to all of you. Yes. Yes. On behalf of our webinar team of Sarat Chandra Pawar College of Pharmacy, I welcome here to all the participants for this today's webinar, and the special welcome and thanks for Ashwin Kuchekar sir for this acceptance, which is somewhat different, because always we are thinking somewhat different to give to all the participants. And today also, Ashwin sir, near about 1500 participants are over there who are being registered, and near about you would be very happy to listen that near about 48% of the faculty has been registered for this today's webinar, means, and near about 50% of UG and PG scholar students and some research scholar students are also being registered for this today's webinar, and near about 2% others that are from the industry people, they are being registered. I would like to all the participants, I would like to give the brief introduction of our today's speaker, our resource person, Dr. Ashwin Kuchekar sir, who has completed his graduation from Pune College of Pharmacy, Bharati Vidyapit, Pune, and master from R.C. Patel College of Pharmacy, Shirpur, from North Maharashtra University. And he has completed his doctorate also in the subject of pharmaceutics from Pune College of Pharmacy, Bharati Vidyapit again. Even during his research work, he has got the CSR, SRF, CSR Senior Research Scholarship or Research Fellowship during his research works. And he is having a huge industry experience also, where he has worked for the formulation and development department wherever he has been joined. He was from the Abbott Healthcare Pharma Private Limited, even the Lupin Research Park, Pune Limited, where he has worked for the QBD and Formulation and Development Department. Even he has been served for the Piramal Healthcare, Girgaon, Mumbai, and even the New Life Pharmaceutical Sciences at Pimpri, Pune, where has been worked for the R&D departments and even food and F&D departments. Even if you see his achievements, actually are also again somewhat very different, because with his biodata, each and every word is readable and it should be known to you, because he has been successfully, what about his achievement, he successfully completed the scale up batches of diclofenac injections at New Life Sciences, Pentop Sahib, Dehradun, India. And also he was being a part of the part for the successful completion of commercial launching of octandine hydrochloride mouthwash at Winlabs Biotechs, Dehradun, India. Even he is the board of study member of Savitribai Phule Pune University, and he has also bagged one prize of Young Scientist Award from Video Good Professional Associations of the India. And he has delivered the number of the seminars and the lectures and as a resource person at numbers of the places. And today we are very happy to you, Ashwin sir, also to have such a great speaker and to have some different type of the knowledge for the particularly for the PG students or the PG staff members, those who are working with the software and all that. Without taking so much time, I would like to request Ashwin Kuchekar sir to take the charge of this today's webinar. Towards Ashwin Kuchekar sir.
Yes, sir. Yes.
Yes.
First, I'll share my screen.
Yes, sir.
Sir, is my screen visible, sir?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah.
Yes.
And am I audible?
Yes,
Yes,
sir. Yes, you are
Yeah.
properly.
So, good afternoon, everyone. Ashwin here. So, thank you, sir, for such a nice introduction. And it gives me a great pleasure to deliver a webinar on such a great platform. First of all, I would like to thank the organization and management of Sharad Chandra Pawar College of Pharmacy and Principal Dr. Dama sir for giving me an opportunity to share my thoughts on this platform. Thank you, sir. And without the further delay, I'll start my presentation. So today's topic for this webinar is response surface designs. So the agenda for this webinar will be divided into two parts. First is introduction to experiment, steps and objectives in experiment, response surface design, which is our main part, that will be central composite design, and Box-Behnken design. I will then shift towards the Minitab tutorial, where I have made the screenshots of the steps which should be followed into this using during the Minitab software. So I would like to start with some brief example that why exactly or why do we need this design of experiments, or why we have to study this response surface methodology, or from where this term response surface methodology it came. So we all know that if you look at this picture tells us that there is a small plant which is in the mud and there is a pot which is watering there. So from this we come to know that yes, this is a plant which is to be grown like a tree, but how and why and it will be grown like a tree. So there are many factors which should be considered. So those factors can be how much water is needed for this plant to grow, when to add water to this plant, what type of mud should be used, what type of pot should be used, it should be in the garden or it should be in the pot, it should be in the garden or it should be in the inside of our home, whether it should have a cover or it shouldn't have any cover, or with and without fertilizer it needs to be grown. So the same factors, if we simulate it into our pharmaceutical dosage forms with different types of dosage forms like solid, liquid, semi-solid, then we come to know that yes, the factors which were there in the first example are correlated with the factors that are responsible for the quality of our pharmaceutical dosage forms. Now, if you consider different dosage forms, those different dosage forms can be solid, liquid, or semi-solid dosage forms. Now, if you consider one dosage form amongst these, how much of water, if you correlate it, how much of solvent do we need? How much of organic solvent, aqueous solvent do we need? When to add? If we are going for a specific method, should we add wet granulation? Should we add aqueous? Should we add organic? Which type of mud, which type of excipients do we need to add into our different dosage forms? What type of pot? If you relate it with our pharmaceutical dosage form, which type of packagings do we need to do? Do we need to select? Is it hygroscopic? Is it light resistance? Is it susceptible to different conditions? depending on that, different type of packagings needs to be done. What type of cover, as I said, different packagings. With and without fertilizers. Is our API a bitter API? Is it an odor API? So do we need to add something flavoring agents? Do we need to add different test masking agents? Do we need to add different excipients for sustained release or controlled release? All this, when we think and we implement it, we get a quality product. And this quality product needs to inhibit the instability into the product. And this quality design of a product is reflected into the quality by design. And in this quality by design, we will turn on to the response surface methodologies. So from where this quality by design term came? So this also tells us that it is from the Six Sigma. Six Sigma is nothing but it is DMAC: define, measure, analyze, improve, and control. And when we have these tools, we can give an approach of quality. And if that quality is inbuilt in our experiment, then it will be a design of experiments to do a quality product or to develop a quality product. Now, let us start with our actual presentation, which is why do we need, or why design of experiments are needed. So first of all, if you consider a dosage form you want to develop, then there are different relationship between the input factors and the process and the formulation factors. So the first thing is identifying the relationship between cause and effects. So what will be the compatibility within the input factors? What will be the relationship between cause and effect? What will be the relationship between the input and output? Also, it is used to identify the optimum formulation and concentration of excipients. Yes, we know that yes, a development can be formed or developed when we have some excipients into it. But which type of excipients? How much ratio of the excipients? If you are using one excipients in two different parts, if you consider intragranular, extragranular, if you consider a liquid dosage form, which type of excipients and in which concentration, what will be its level? So this is why we need to study, or we need to discuss why we should use design of experiments. It is also used to provide an understanding in the interaction between the causative factors. Is there any interactions? If there are interactions, remove them initially. If there are no interactions, if they are compatible, go on, proceed with your trials. Determine the levels at which to set the controllable factor in order to optimize the reality. Yes, we have to determine the levels. And if the levels are determined, it means that a design space is determined. It means that age is determined, a limit is determined where we have to work within those limits. It also helps in minimizing the experimental error. Yes, we now say, we discussed that yes, a design space is determined. So if we are going out, the chances of error will be increased. If you are working in the design space, we are working within the limits, we can say that there are minimization in the experimental errors. So we can save the time, we can develop a cost-effective product and improve on the robustness of a quality or of a product or a process in the variation. So these are different steps where we should consider why design of experiments are needed. So when we have discussed that design of experiment, why design of experiment, now let us see or understand what exactly is an experiment. So we say that experiment is nothing but performing a scientific procedure to determine something in a laboratory. Yes, we do perform different experiments in laboratory, but those are scientific experiments. And those scientific experiments are manipulated. Manipulated means what? They're changed. There is something transformation in the process, which is taken place because of the input and the process. And we get something that is called as response. We get something that is called as output because of something transformation from input with help of some process to output. So this is what is experiment. So let's take a simple example, which we say that it's a common example of a game, which we say it's a cricket game. We take an example, two captains, they come to the umpire tosses a coin. Means what? Umpire tosses a coin is an input variable, he tosses the coin, that's a process, and the output what they get is head or tail, and that head or tail will depend or will select or tell us or result us in saying that yes, the particular captain will go or opt for batting or cricket or bowling. So this is a simple example. Now, why not correlate this simple example with our pharmaceutical dosage forms? So experimentation plays a role in developing a dosage from a lab scale to a scale-up batches. Means if you are developing a product or you are developing a research or preparing or doing a research or performing a research in a lab scale, This design of experiment will help us to increase or to scale up the batches up to the commercial batches. So let's see, it will help us in designing the formulation and product design. Yes, during design of a product, different formulation variables, it may be some different excipients, it may be CMAs, what are called as critical material attributes are need to be considered. Different process parameters like critical process parameters, CPPs, which will be there when we will be using manufacturing and process designs. Different process improvements, if there is something improvement needed during the process, then during the intermediate development, intermediate process, we need to improve the process so that the further or the final product will not be hampered. So this is how the experiment term is defined. So in short, I will tell you the test of series where purposeful changes are made to identify a certain change is called as an experiment. So this is what we will be discussing throughout our experiment, and this will be the heart of our presentation, that there is input, process and output, and it will lead to a different series of purposeful experiments. Now let us understand what exactly is the process model. So process model is what is, I want to prepare a finished dosage form. It may be of any dosage form. It may be solid dosage form, it may be liquid dosage form, or it may be any semi-solid dosage form. So why not understand that for developing a finished dosage form, for developing a solid, liquid, or semi-solid dosage form, the first thing I need is inputs. The second thing I need is the process. And the third thing I need is the outputs. So when I know this input variables, when I know the process variable, I can define my target, that is my outputs. So in QBD, there is a term that is called as QTPP, Quality Target Product Profile. Now let's learn that what are different inputs. So inputs will be my API, my raw materials. API in terms of, let's take an example of a solid dosage form, tablet. Let's take an example of metronidazole. I'm taking an example of metronidazole, and with API metronidazole, I have some raw materials, like consider as an examples like diluents, CMC, MCC, HPMC, diluent filler, disintegrants, and lubricants. And when I input these raw materials, when I input this input materials, I have to get some output that will be a tablet dosage form. And that tablet dosage form which I get will have some formulation specification, as well as it will have a process specification. Now this formulation specification will tell us that the levels of the dosage formulation variables, the levels or the limits of my dosage forms, or the limit of my excipients, the limit of my drug product attributes, assay, DISO, impurities, different things this formulation specification will tell me. It will also tell me different process specification. In process specification in terms of which type of method I am going to utilize to develop a IR dosage form, metronidazole IR dosage form. If I'm using a wet granulation method, if I'm using a compaction method, if I'm using a direct compression method, that all its parameters, critical process parameters will be depicted into the process specifications. So there are controllable factors and uncontrollable factors which will be responsible for the outputs. And let us see that control factors will be speed, addition rate, including API, raw materials. And the uncontrollable factors will be temperature, different operators. In production plant, if you go, there are different operators, different knowledge, different training, different educations, and those are uncontrollable. The temperature, decrease in the temperature or increase in the temperature may not be controllable, because when you start decreasing a temperature, we have to wait for some time, or that can't be controlled at a specific limit. So these are the control factors and the uncontrolled factors. So if I say, or if I term these control factors and uncontrolled factors as X and Z respectively, then I can say that my output Y will be an equation which will tell me that Y is function of X. X is what? Controllable factors, including my some properties of uncontrollable factors, that is Z. So if I now to say that my output Y is function of inputs, means if my inputs are changed along with this controllable and uncontrollable factors, my output will be changed. And simultaneously, my process specification will change, my formulation specification will change, and my finished dosage form will be changed. So to maintain that, I should know first the functions of my X, functions of my input or the control factors. So along with these control factors or along with these controllable factors, formulation factors, we also have to consider the process factors. The process factors can be process controls, process inputs, process outputs, and process defects. If I am saying that I am using a wet granulation method to prepare a dosage form, I say that during wet granulation method, there is RMG, rapid mixing granulator I will be using. And that rapid mixing granulator will have different parameters. I will have some different parameters like kneading time, binder addition time. What will, during lubrication, I will say that lubrication time, number of blending, number of RPM. This will be my different process variables. And once these process variables are set, I can say that my process is a quality process. And this quality process will give me a quality dosage form. Along with, I can say that if I am considering two factors from controllable factors, X1 and X2, then equation along with this general equation will give me y is function of beta 0, beta 1, X1 plus beta 2, X2. Means these are my factors, and these factors will give me a y, a quality y. And when I get this equation, I will say that this equation should be a normal density function, means it should be a significant, or else if those are insignificant, there will be no use of this process. And if this is significant, I can say that the desired value is obtained, and this desired value will give me my experiment, a complete experiment. And I can say that by all these factors, including all these factors, this will be a quality dosage form. So if I say this is a process model, let's transform this process model into a block format. So I say that yes, temperature and reaction time, this is a temperature, this is reaction time, which is in terms of 2:2 factorial design, as well as these are the process factors. So here you can see 4 different factor points. This is 8170 is one factor point, 8180 is the other factor point, 9180 is the other factor point, 9170 is the other factor point. And this is the block diagram which we will be studying with help of the process model, which we have discussed in earlier slide, into our different responses. Now different responses improving of the yield of a product. Now this is what is a simple mechanism, that input, process, and outputs. The inputs can be chemicals, temperature, reaction time, what we have discussed, and the output is the yield. And when I will get this yield, if I use these input variables in a good manner, or in a specified manner, or in an optimum manner. So let's go. So before discussing this, there are different models or different tools by Six Sigma. Those says that a DMAC methodology or DMAC tools needs to be followed. The Six Sigma says that define, measure, analyze, improve, and control. This is the general flow. But when we go into design of experiments, we need to follow a describe, specify, design, collect, fit, and predict. So these are different tools we need to be followed. So once we have known to what is process model, once we have known what is the experiment, and once we have known what exactly is the block diagram, let us start with the steps that are used in the experimentation. Now, as I said that like DMAC, there are different steps that need to be followed during experimentation. So first is define a practical problem. So defining a practical problem sounds easy, but it is not that much easy to actually define a practical problem, because none of us define one practical problem. And if we define one practical problem, when we start with our exact experimentation, we go somewhere else and we find out the other practical problem and we work on that. But to make that easy, to identify the practical problem, I suggest that the Ishikawa diagram is the best suitable diagram which you can use and find out that this was my practical problem, and these were my different M's, or these were my different responsible factors which were responsible for this problem, and that will make you easy to define a problem. So after defining a problem, give your objective to the experiment. So objective should be specific. If I say that there are inputs, there is process, there is output, and my objective is to maximize my process. Maximize my process means what? I have to maximize my drug release. The other objective can be minimize, minimizing the impurities which will be occurring in my dosage forms. So there will be maximize and minimize. Based on the objective, you need to define a problem, and then you need to define the treatment runs, materials, and the process. So the third point is select treatment runs. Now selecting treatment runs means select the input factors like controllable factors and uncontrollable factors. So before selecting this treatment runs means selecting before selecting this controllable or uncontrollable factors, we should be well prepared for the experiment, that yes, this is my experiment and these are my input factors. Just for sake of just increasing the number of factors to fit for a design, we should not select this controllable and uncontrollable factor, the numbers. First identify the numbers, then select for the design. Select the experimental methods. Materials, so experimental materials can be in CMS, critical material attributes, or critical process parameters. It can be into amount, concentration, levels, or the process parameters. The next point is select the experimental design. Now, once you have finalized with the runs, once you have finalized with the input factors, once you have finalized with this process parameters, then select which type of design will be well suitable for your selected parameters or selected variables. You can go for OFAT, one factor at a time. You can go for multiple factor designs. It depends on the number of factors you have selected. It can be 2 level, it can be 3 level, it can be central composite design, it can be factorial, it can be Box-Behnken design, it can be mixture design, it can be de-optimal design, different design. If you want to have a defined number of materials, initially go for screening. A different selected number of parameters from a large number of parameters or a set of parameters. After selecting this, select an experimental unit and number of replications. Now, number of replications is the principle of experimentations. This replications we will be discussing into our coming further slides. So just hold on to this replication. We will discuss this in the first further slides. Next is ensure proper randomization and layout. So randomization means the trials which you performed based on the design you have selected should be randomized. This is the other principle which is used during experimentation. Randomization and replications are discussed in our further slides. We will go there. The next point is ensure proper means of data collections. Yes, data collection can be online, can be offline, can be manual. It can be based on the sensor data collection. It is dependent on your type of process, type of equipment which you are using. If that equipment is an automated equipment, you will get an online. If it is an inline or online equipment or experiment, you will get all the designs there, all the results there. So after collecting the data, outline the statistical analysis and then do the experiment. Conduct the experiment, analyze and predict the experiment with help of statistical analysis tools like ANOVA. In ANOVA, you can go for significant value, p value, r square, and all. We will be discussing it in our further slides. Then finally, prepare a complete and readable design of experiment reports, which will tell you the design space where you have worked on, and that the readable reports or the DOE reports will be useful for you to determine the specifications for formulation specification or the process specifications. So don't wait till your data is complete. As soon as you get the data, start analyzing, start predicting, or start utilizing the time for the statistical analysis. So now, once we have understood the steps of experimentation, let's focus on the principles of experimentation. So as I said, randomization is one of the principles. Let's start with randomization. So randomization is the manner of allocation of treatments to the experimental units. Means you have to allocate some treatments, some runs, some trials, some experiments at a different time, at a different treatments. So in short, it's a statistical tool which controls the biasness and other sources of extraneous variation which are not controllable. Means it controls the noisy factors which are uncontrollable factors, and that should be divided into all the runs where you will be randomizing it. So let us take an example. Our example is input, process, and output, and the example is of chemical process, and chemical process has time with respect to 80 and 90, which is its time low and high. Temperature is 170, 190 low high, with the center points 85 for the time and this 180 for the temperature in terms of Fahrenheit. And let's plot a block diagram. So when you plot a block diagram, this will tell us that you have 4 different factorial points. Those are 8170, 9170, 9190, and 8190. So these are your 4 factorial points. But is it that we have to run these 4 factorial points as such? Do we need that this combination setting should be followed or treated as such, or which trial should be conducted first? Is there any order? No. In randomization, there should not be any order. Perform them randomly. So if I want to perform them randomly, what I will select? I will not select sequentially from this trial to this trial to this trial to this trial. I will select 1 number trial, then this 2 number trial, 3 number trial, and the 4 number trial. But if I say that I have to perform 2 runs for 1 trial, and this 2 runs for the other 3 trials, then it should be in a random manner. Means 1 trial from the treatment 1 or 1 run from the treatment 1 should be done per first. The second run from the second treatment should be done second, third, fourth, and simultaneously and sequentially. So when you perform these trials, you will get total number of 8 runs, because 2 plus 2 plus 2 plus 2, and you will get total 8 Ys. And these 8 Ys will help you to give you a random variable. But if you select as such that 2 trials from 1 treatment, it will not be a random trial. Now, why is it so, or why should we follow this randomized experimentation? Because sometimes the materials which we get, or the excipients which we get, or the material attributes which we select, depending on the excipients, depending on the materials, may vary, because that may not be same for 1 trial. And if the material is finished and you are taking for the other trial, it may not be the same. The specification with respect to the attributes may be different. And if I do so in 1 trial, then my 1 trial will be biased and my other 3 trials will be different. So the biasness will be there, but the biasness will not be distributed in this whole trials, in this whole runs. So it may be that sometimes that if the experimentation is going into a production unit and there are different operators and the runs is for different large number of time, and the different operators are coming, and based on the different operators education level, there is change into this operations. So we have to divide all these uncontrollable factors uniformly, and so this randomization is important. So randomization will be followed for a probability distribution. So this is what is randomization. So the runs should be performed randomly, and randomly you have to select Y, and based on the factors you will select, you will define the equation for the experiment. So that equation, we know it is a general equation. So the next principle was replication. So the replication means repeat the entire experiment, but don't change the factor setting. Means you have to repeat the entire experiment, but many of them you get confused between replication and repetition. So replication here is to be done with randomization, and repetition is done repeatedly in a continuous one go. So replication here, what we are discussing, it should be done in a randomized manner. So if we take an example of 4 factors, at least 1 experimental run to be performed, then we'll get 1 Y. And if I say that all experimental runs, if I am going to run at 1 time, I will get 1 Y, but which will not help me to find what are exactly the errors into my experiment. So this is not called as an replication. So what is replication? Let's go. So take the same example, a block diagram. Here the numbers are randomized, because replication is repetition of entire trials with respect to randomization. So now let me consider the same parameters, 80, 90 for time, and 170, 190 for temperature, and these are my 4 factorial points at 4 different corners, and those are divided into 4 randomized points. So what should I do? I have to replicate. So I should have some amount of runs. So I select that I have 5 number of runs for each factorial design. 5 runs here for 1 treatment, second treatment, third treatment. So 5 into 5 into 5 into 5. Then how much does it sound? So that much amount of trials need to be performed at 5 runs should be there at a constant setting, at this setting. But this setting should be remain constant, but randomization should be followed. 1 trial from here, the other trial from here, the other trial from here. So sequence 1, 2, 3, 4. Sequentially, it shouldn't be there. It should be a randomized trial. So I will get 5 runs at a constant setting, which will be called as replication, and which will help me to find or to develop a precise and accurate product with a robust process. So then that experiment will be called as replication. So to have a clarification between replication and repetition, I will repeat it again. Replication is continuing or repeating the same factor or the entire experiment by not changing the factorial setting with respect to randomization. But if I say that repetition, the same combination factor settings are repeated at the same experimental run at one go. Means you have to start for repetition for 5 trials at one treatment continuously. You don't have to randomize them. So this is the difference between replication and randomization. So let's go for the third principle in experimentation, that is blocking. So what does this blocking means? So blocking is to increase the precision by breaking the experiment into homogeneous materials. It is based on different materials, based on different operators, based on the block variability. Means if you consider one material, if you consider one excipient, you consider one API, those APIs, those excipients are of different batch numbers, different manufacturing lots with different specifications. So for a specific batch number, specific lot number, specific product specification, prepare a group, and that block will avoid the more variability into the experimentation. So the purpose of this is to increase the efficiency of experiment and arrange them in a group or a block. So example of this is certificate of analysis, COA of API, where the terms or specification like PSD, particle size distributions, are maintained. Polymorphic forms are there. Sometimes the method is there. If you say that the particle size distribution is ranging from 2 to 5, and the other lot says that it is ranging from 3 to 5, there is something change. But what that change is bringing any difference in our experimentation, that needs to be checked there. And shift-wise operator, which are uncontrollable variables. So the raw materials supplied by different vendors has different specifications. There are different operators. Different companies provide one excipients, one API. So do we need to take one block, one vendor, one API continuously throughout the experimentation, continuously throughout the development of a product? That needs to be done there. So it will help us in minimizing the error term and increase in the quality of a product. Or if we are not following that, the error term will be increased there. So this will help us in making the homogeneous material. Breaking that homogeneous material into different blocks is nothing but blocking. So I hope this blocking is clear. The fourth point or fourth principle is confounding and aliasing. So these are the multiple effects, those are tied together into one parent effect. So this is somewhere it is considered when you are using two different excipients with the same property, and you are getting one excipient like the synergistic effect, and we are not able to identify whether this property or that impact on this response is because of either or from these two excipients. So that is a parent effect, but that cannot be separated. So you can take an example like two persons tossing two different coins. So whether you are just tossing two different coins, but we are not sure that whether the two persons are with similar pressure, similar RPM, similar coin, different coin, what is the weight of coin, which coin it is, different. So, and if you are getting it, then you are getting either head or tail, and that is called as a compounding effect or a together effect. And these are different principles. So these were different principles, and let's discuss terminologies before starting into deep for response surface methodologies. So different terminologies for this design of experimentation are treatment combinations or experimentations, which are called as the runs where all factors are specified at a level. Means our actual run, which has some levels into it, and those are to be run for an experiment. Now, what are factors? Factors are the variables that influences the formulation of process variables. Here you can call those factors as the input factors. It may be formulation variables, it would be process variables, but those factors need to be assigned with some specific levels, assigned with some specific values, and those are called as levels. Sometimes those are with some mg values, percent values like concentration, amount, percent, or ratios. If you are using cross-povidone as a disintegrant into intra and extragranular, then it will be a ratio for cross-povidone, ratio in terms of 5:5 or 3:2 intra and extragranular ratio. The second factors are independent variables. Those are input variables which are directly under control of the product development scientist. So these independent variables are sometimes qualitative or quantitative. So we will discuss what is qualitative and quantitative. Other or the opposite to this, independent variable x1 and x2 are the dependent variable, that is y, and those are characterized or characterization or characteristic property of the finished product. So those are y's, those are response, those are outputs, and responses are properties of a system to estimate the outcome of an experiment. So these are responses. So when you say that quantitative variables and qualitative variables, the difference is quantitative variables are numeric. And so in design of experiment, when you use different softwares, you can type there numerically as well as categorically, like high, low, medium, or fast, slow. When you go for RMG, there are two different options, low and high. There we don't have any RPM, so there you have to set as low and high for this RMGs, rapid mixing granulators during wet granulations. So these are numeric, like time, temperature, amount of polymers. Categorical variables like grade of polymer, lipid, excipients, or tableting machine. When you go for compression of tablets, there are different types of tablet, different toolings of tablet. Tooling tooling B, tooling D, different depends on the left LHS, like low left hand side compression and right hand side compression, means left hand side punch, right hand side punch during commercial batches. So these are different terminologies which are used in design of experiments. Now let's start with objectives of design of experiments. So there are different objectives for designing an experiment, for exactly for which objective we are starting our experiment, like comparative objective, screening, response surface, or mixture. Now here we will be focusing on what are response surface objectives. The parts are like comparative. If I want to compare something, if I want to compare the several factors which are there into my experiment for getting an good output, so I will compare it with less and more or less effect. If it is a screening objective, means I want to screen the different 10 number of excipients for significant and insignificant parameter, or a highly impacting or insignificantly impacting or low impacting parameter or variable, then I should go for screening. I should select the significant factors and then shift on to exact factorial design or response surface design. The next is response surface objective, which is response surface variables with respect to the levels, -1, +1, like low, middle, high. And mixture objectives are when you have some mixture of different excipients which leads to the equal for 100%. Depending upon this different type of objective, which objective we are to be focused, you need to select that objective, select the Y, select the levels, and start with the experimentation. Now let's start with the basic part of the experimentation. After knowing the objectives of experiment, we'll start with 2 raised to k factorial design. Now what is 2 raised to k? So the term that is called as L raised to f. L means levels, F means factors. 2 raised to k means 2 levels, k factors. Now let us have a similarity or clarification with respect to 2 level factors or 2 level experimentation designs. So here you are looking at the 2 factors A and B. So these are different equations or different equations that will be designed after setting a design of experiment, like A, B, and AB. But if you consider a 2 level but with 3 factors, it will be A, B, and C, and you will get different treatment combinations. With respect to this, there will be less number of runs. But if you consider 3 levels, I'm talking about 3 factors. I'm talking about these 3 factors because we will be focusing on the response surface methodology and central composite design, which are within the response surface methodology, where 3 factors are to be considered. So if I say that for A, B, and C, I have 5, and 4 different number of combinations, then I need to do 100 different settings, and the trial combinations will give me, after replication of 5, will give me 500 experiments. So is it so that I need to perform this 500 experiments? Doesn't it sound a huge number of experiments to be conducted? So what shall I do? So there are many factors. Shall I reduce the levels? Shall I reduce the factors? Or shall I change my design? Huge number of factors, it will not be able to conduct the experiment. And yes, if I want to perform an experiment, I should select a design, select the significant factors only, which will help me to reduce the cost, reduce the time, and make my product a robust product with a precise process. So this is the base where we will be starting with our response surface methodologies. With keeping this in mind, we have to reduce the number of runs, but select the more significant parameters. Those are impacting my product, or I can say the quality product. So let's start with response surface methodologies. So response surface methodologies, the terms or the objective for this response surface methodology is, first is identify a value, predict a value. You have to predict a value based on the surface. So in response surface methodology means there is a surface where there is a method to determine the response in which direction it is, whether it is in a plus direction or a minus direction, whether its shape is in a simple hill type of shape or a valley type of shape. So the prediction value, it can be found from the estimated surface if the surface is shaped like a simple hill or a valley hill. Okay, the second objective is direction of the surface. So the surface which is there into response surface plot will help us along with the shape to identify the direction in which direction we should proceed. So the shape of the surface can be analyzed to indicate the direction in which new experiments shall be performed. The third objective is optimization of the response. Mapping a response surface over a particular region of interest, selecting an operating condition to achieve specification or customer requirements. If I want to do a response surface methodology for a redevelopment product and I know where the feedback was and I want to redevelop a product, I should first say or take into consideration that where was my operating condition, or where should be my operating condition. It should be inferior or a superior. It should be near to the optimum zone or it should be away from the optimum zone. This I should map first with the interest of the customer requirements. So that is called as optimization of response. The fourth objective is developing a process. So once I know what is the optimization and all, predicting value, once I know what are the response surface and the shape, I should understand the process. I should understand the scale up and technology transfer process that will make my process a robust thing. Now here, process term is of two types. Process one is where you say that it's a manufacturing process, and the other process term is where we say that it is transferring the input to output. So there are two different process terms which we'll be considering here. So improving the process means we will be troubleshooting, we'll be focusing on the troubleshooting process problems and the weak points, which will help us to neglect the uncontrollable factors and take into consideration the controllable factors. So these are the objectives. The last objective for this RSM is optimizing the process for formulation. Now, yes, optimization here comes with a great deal, that it is maximizing or minimizing. You know that there are different response surface shapes where you might have seen that either they are going into the valley type direction or either they are coming into a hill type direction. It depends on what type of response you select. It depends on if you are selecting a process yield. It depends on if you are selecting a % drug release, then a maximization should be followed. If you are selecting a degradation properties like impurities, minimization should be followed. If you're seeing the growth of some instability or growth of some caking in or the crystals into your formulation, you should select the minimizing. Or you're seeing the particle size increasing, and if your formulation is prone to increase in particle size, then you should select a design where you should minimize the formulation or optimize the process by selecting a minimizing process. The next is find out an improved or optimal process setting. To find out conditions where the result of the process is insensitive to the process variation, the process being therefore robust. And to make a robust process, we should go and select this, take into consideration all these objectives and follow an response surface methodology process. So once we have known what are objectives, let's start with the process. Now, keeping the objectives in mind, we will start with the response surface methodologies. Now, what is this response surface methodology is? Response surface methodology is collection of mathematical and statistical technique, where you will collect data, mathematical data, and apply a statistical tool with respect to 3D response surface plot, counter plot, or else ANOVA, and you will combine them, and that is called as the response surface methodology. The purpose for this is to optimize the process outcomes. Process outcome means the output variables. You have to optimize this, because if your input variables like X are going to change, it will ultimately affect your Y, that is called as responses. So set the controllable factors in such a way that the response on surface is maximum or minimum. We have seen this. So in other ways, work at an optimum or a desired value, which is our area of interest. Let's consider an example. Take a simple example, which was input, process, and output. Now I say that yes, the responses, as we have discussed, should be minimum or maximum. The responses should be Y, it should be yield, it should be maximum. If there are impurities, it should be minimum. But whatever those the impurities, whatever the Y's are, whatever the output variables are, those should be an optimum space. So first of all, I should say that how should I select or how should I keep these controllable factors to have this optimum output, or what will be the relationship of the input variables to get the optimum output. So these 2 points are the main points where we should focus first to get an optimum zone or a design space. If we are not knowing the relationship between this input variable or cause and effect, or if you are not understanding what should I keep the controllable factors or how should I keep the controllable factors, we will not understand where the optimum output we will be getting. In short, you should understand the current operating condition and the region of working or optimum conditions. So taking this into mind, we will see that this response surface methodology is a sequential process where we are at a point on the response surface either that is far away from the optimum, means there is no curvature, that is called as first order, means it says or it speaks only about the main effects like x1 and x2 factors. The objective is to lead the experimenter rapidly and efficiently in the vicinity of the optimum, means the experimenter should perform the experiments in such a way that our design space or the optimum value should be in the center. Now once the region of optimum is found and more elaborated, it is in the term of second order model where we can locate the optimum points. Let's take an example. You have an example which says that there are two variables x1 and x2. This have different nature with respect to their property, excipient properties. You may consider it as sodium carboxymethyl cellulose or cross povidone. Any example, I have considered here as SCMC or CP, and one response which is drug release at 4 hours. Now my response should be nature should be maximum. It should not be minimum. There are two types of nature. As I said, for drug release, it should be maximum. And the results I should get, it should be either first order, it should be either second order, or with higher order quadratic effects. Means when these are input variables, y will be function of x1 and x2 with some e. E is some negligible errors. Means y will be function of sodium carboxymethyl cellulose and cross povidone. Means my percent release will be function of this two. If these two factors are changing, my y will change. If I'm getting this response surface plot, it tells us that it is a first order and it is a main effect plot, means it has only the main effects like sodium carboxymethyl cellulose and the cross povidone. But if I get a response surface plot with some curvature into it, it will say that it's a second order plot having some curvature and quadratic terms, and that will be called as the second order terms, and its equation will be different from that of the main effects equation. Means the first order and second order equations will totally be different, and what we get is during designing or during using the softwares, we get sometimes by default a linear model, we get sometimes by default a quadratic model, and that model tells us that the response is governed only by these two factors and no quadratic terms are involved. And if you get these factors, it selects that there are some quadratic term involved, and it should be there, because if you're going for response surface methodology, the quadratic term should be there, the curvature term should be there, and then it will be called as the response surface methodologies. If you're getting this type of graph, it will be just the main effect graph. Okay, now when you actually want to start a practical, or then just we have to find out that where exactly we are working. Suppose now let us consider that I am working in this direction where I am unknown. I don't know whether this direction is a operating or optimum condition or not. Suppose I am operating here with respect to the previous experience or previous history of those excipients. I am starting my experiment from this. But when I perform this, this will be called as the current operating condition, my current operating condition where I'm using or where I'm operating. When I start with this, there were steps into our design of experiment. We said that once you get the data, start analyzing it. Don't wait for anything. Don't wait for the other data. Once you have one experiment trials, check to this and check whether this trial was performed in an optimum direction or not. And if it wasn't performed, then where it should have been performed. So these counter plots will tell us whether the direction or the surface will tell us whether the shape or the direction of improvement was. Now, if you see here, the values are there, and those values denotes the direction of improvement. So if this is current operating condition where I was earlier working here, then this current operating condition, after analyzing the experiment, I came to know that this was 500, 550, 600, 700, and then 735. Means the values are increasing. Means this is the direction of improvement where I should actually perform this experiment in this direction from current operating condition to the region of optimum. And this is what we usually forget. If we start performing experiment in this current operating condition, we get some irrelevant data, but we say that yes, even though my center points, 0 points were good, it was not able to achieve 98% for drug release, because this is the reason. From first trial, we will come to know that yes, the direction of improvement was somewhere else and I was performing somewhere else. So using this RSM, we would find out the operating procedure. The shape and the values on this response surface plot will tell us where we should exactly move from this current operating condition, where we should move to reach the optimum region. So this is the technique to understand that whether we are performing the response trials, whether we are performing the 15 number of trials, 27 number of trials for CCD, or n number of trials, whether those are in a desired pattern or not. So this was about RSM. Now, once you start or analyze with the RSM, you will get counterplots and response surface plots. Now, what does this counterplots or counterplots denotes? So these counterplots are the graphical techniques. These are 2D format techniques where there are Z values, the lines that are connecting the X-axis and Y-axis, and this counterplot is formed by different independent variables which we are selecting. It will be different based on the experiment what you select, and these lines are called as the iso response lines. Means these lines will help us tell the prediction for this response. In short, the definition for counterplot, we can say that it is the lines that are joining the equal points which are having the same number. Now you can see in center there is a dark circle, but it is not in a spherical form, it is irregular shape. But this has completed its line, it has joined itself. So if you consider the line which is apart from this, it is of different color and different shape. If you have moved this graph, you would have seen it would have more clarifiable to understand this lines are been joining. So there are different types on what we have to interpret these counterplots. So this each line has different values, and if there is, you see the distance, this is called as reduced level distance, and that is called as counter interval. So this is very low, so the steps or the runs that can be used to increase the function will be less. But if you consider the center circle and this line, these are far enough. So if you want to reach till here, you need to do more number of experiments to reach this line. So this color tells us, indicates that these are the high values. Means if we were operating somewhere else in this left hand side corner, we need to have gone till this dark circle where there are high values, where exactly my optimum region is. These are reduced level, these are lines, and this graph, this right side point graph tells us that difference in the shades of color with respect to the difference less impacting on the response. So this is what is the counter plots. In short, if you have straight lines in your counter plots, it will show you main effects. But if those are with curved lines, those are with presence of the interaction terms, means those are with presence of the second order model, and those are with presence of some response surface, either with different shapes. So there are different shapes for response surface. We have discussed that there is a hill shape and a valley shape, but there are different shapes with respect to maximum, minimum, radial, and rigid and saddle. So let's go further. So the counter plots are over. Now what is exactly a second order model? The second order model is a very flexible model. It takes a wide variety of function forms. So it will be often work well as the approximation to the true response surface. It is easy to estimate the parameters like betas in the second order model. The second order model works well in solving the real responses of the problem. So after you get this counter plot, you get the 3D response plot, then you get the equation But this equation is something different from the equation which is there for the factorial design in terms of addition of the squared terms. This equation is used to model the curvature, because if this square term is there, it will be second order model, then it will be a curvature term. To estimate the interaction and even quadratic effect, this equation is used to determine the shape. It is used to understand the mapping region of response surface. It is used to find the levels of variables that optimize the response. It is also used in selecting the operating condition where the exact direction of improved region of optimum is. The response surface equation model depicts the change in the variable that affects the response of the interest. Means in short, this is the equation where there is presence of addition or presence of the square terms, or we can say the quadratic terms, x square, x1 square, x2 square. So as we discussed, there are different shapes for response surface plot. Those are ridge, saddle, maximum and minimum. Ridge is somewhat slanting towards one end. Saddle is the two corners, two ends of the response surface plot on the upper side, and the middle part is on the bottom side. Minimum is just like a valley, and maximum is just like a hill. So based on this response surface process objectives, there are two different types of response surface designs. One is central composite design. So this central composite design can fit a full quadratic model. Yes, because response surface models are the models which fit the quadratic models. This is used when the design plan calls the sequential experiment, because this design includes information from a correctly planned factorial design experiment. Means the central composite designs are augmentation or continuation of the factorial designs, and this includes the runs from the factorial experiment. Now this we will see what type of factorial designs are there and how these factorial designs are included into central composite designs. The second type of response surface design is a Box-Behnken design. However, few design points than central composite design, because this also covers the three factors even more, but has less number of designs as compared to the central composite design, because it doesn't include the factorial experiment. It includes the three different levels: -1, 0, +1. This has three levels per factor, unlike central composite design can have up to 5 factors. So Box-Behnken design never include the runs where all factors are at the extreme settings, such as all of the low settings. So these are the two different types of response surface methodologies, like central composite design and Box-Behnken design. Now let's start with what is central composite design. Now, as I said that central composite design has some factorial design. Now let us consider two different designs with two different variables. Two design variables and three design variables. So this has three factors: x1, x2, x3. This has two factors: x1 and x2. And this is what is the experimental runs which we'll get from central composite design. Now there are three blocks into this central composite designs. Now we have discussed what is block into our principles. The blocks are similar terms which are separated. So this is one block. This block has a factorial points. So these pink points will tell us what is factorial points. So we have discussed this in terms of block diagrams, where four corners has the 4 factorial points. Then these are the axial points for this cube. From this center, and from this front center, it has 3 different axial points. And lastly, it has center points. So from 8 factorial design, 5 axial points, and 3 center points, you will get a central composite design for 3 factors like x1, x2, and x3. Now, these factorial points are with -1, +1 for factorial design. The 0 term is not included here. So these are low and high values. Now, do we say that if I give a central composite design to an operator, will that operator will perform this factorial points like low and high? It will be sometimes that he might not perform the experiment with low. He might perform with this vicinity. It might be not for high, it might be near to the high. So we are not sure whether it was in the center or this. And to avoid this, sometimes we can use or perform this axial points where those are in between this factorial points and the center points. So this these axial points are performed with help of the distance from the center. Now same is with the case with the 2 design variables. Now let us discuss what are these central composite design with respect to factorial, center, and axial points. Central composite designs are useful for sequential experiments. These are for factorial and fractional factorial design with center points augmented with axial points. Sometimes axial points are also called as the star points. Efficiently estimate first order, second order terms. It builds a response surface plot with a curvature, adding center and axial points to previously conducted factorial designs. So there are two different parameters in the design that must be specified. First is the distance of axial runs and the number of center points. So once we determine this, or we define these two points into our design, it will be easy for us to define the distance of the axial point from the center. So what are these factorial points, center points, and axial points? So this is factorial points are the linear terms which are from the factorial points or the factorial designs. Center points are the curvature which will help us give the curvature, and it is denoted by C0, and it is called as the number of center points, either 2, 3, 4, 5, depends on the factors. Axial points, these are the quadratic terms, and this combination of factorial points, center points, and axial points into the equation will give us the equation for the response surface methodology, that is central composite design. Now, what are factorial points? It contributes to the estimation of linear terms and two-factor interaction, because either it will give x1, x2, or it will give x1, x2, and x1, x2, an interaction term. It will contribute in estimation of the interaction term also. What are axial points? Without axial points, only the sum of quadratic terms can be estimated, because the values both below and above the medium of the two factorial designs or levels are ranges from outside their range, and it contributes in the estimation of the quadratic terms, but it doesn't contribute in estimation of the interaction term as like that of for the factorial designs. Now, central composite design with respect to center points. Now, this will provide us the pure error. Means if you increase the number of center points, you increase the number of data, you will make your process more precise and more robust. It will contribute towards the estimation of quadratic term. It will help to stabilize the variance of a predicted response. And the objective of these center points will be to stabilize the response, means to minimize the error, minimize the variance, which is a thumb rule, and to obtain a precise estimate of error, which there will be more replicates and which will be better for our experiment. So this was about axial points, factorial points, and the center points. Now, we say that this for the two factorial central composite design and two factor central composite design. If I say that more the center points, more the information of the current operating condition, more treatment combination will lead to the more information on data. Now let us consider two factorial central composite design, the same function as like that of for the factorial designs which we have discussed earlier. These are the four factorial points, but these are the axial points for this axis and for this x1 axis and x2 axis, different axial points and the center point. So if you have to plot it into a different form, these are the center points. Here lies the axis point, and we say that if the operator is not able to perform at the low level, he might perform between this alpha value and the low value, and that will be the distance from the center point as well as the low values. So these are axial points, and these alpha values are denoted by different formulas for spherical central composite design and cuboidal central composite design. Now we will see what are these types of central composite design. Now, what is rotatability? If it is said that you rotate this block at any distance from the center, the variance remains the same, and that is called as rotatability for central composite design. It is rotatable if the variance of a predicted response at any point in the function of the distance from the center. If you rotate and the variance remains same, that is called as the rotatability. This is the same at point for all the points at different designed corners or different design corners from the design center. So when you start with central composite design, there are different points which needs to be kept into mind, that is region of interest and region of operatability. So you know that this is region of interest. First, you should know then region of operatability. You should perform here so that this is a region of interest. And if you're performing somewhere else here, where is your current operating condition, you will not get this region of interest. And that is the main theme of central composite design. First identify and then start with the range to give for your factors or the variables. Now let's discuss what are the types of central composite designs. The circumscribed central composite design, where alpha is defined or denoted or calculated by k raised to raised to the power of 1/2. For rotatable rotatable or inscribed rotatable central composite design, it is NF, that is number of trials. This k is number of factors. This NF number of trials raised to the power of 1 to the power of 4. Face-centered central composite design is alpha equal to 1 because those are face-centered. So if you see here, this central composite design or the circumscribed spherical central composite design is the largest process space. This design space for this process space of CCC, central circumscribed central composite design, is large as that of, well, compared to the inscribed central composite design. Both this circumscribed and inscribed central composite designs are the rotatable as compared to this face-centered. And for this 3-factor central composite design, points describe a sphere around the factorial cube for this CCC and CII. So these are different types of central composite design. This is the method to calculate alpha. And once you know the number of factors, once you know the number of trials, you can calculate the value of alpha. And based on that, you can have the distance from the alpha, from the center to the axial values. So this is a tabular form where you can say that when this k, this number of factors are 2, factorial points, axial points, and central points, and total number of designs you will get in comparison to the factorial design of 3 levels. So if you see that here, the number of runs in this central composite design, as the number of factors is increased to 5, the central composite design is very less as compared to the 3-level factorial design. The 3-level factorial design is more than 200 designs. And this is choice of alpha. Based on this factorial design, based on these factors, you can calculate alpha. If there are 2 factors, root of 2 means k, by this formula k to the power of 1/2, you will get 1.4. Similarly, for this 3, 4, and 5, you will get different choices of alpha for different types of spherical or rotatable central composite design. Now, if you see this table, this is form of 2 factors, where these 2 factors will tell you that 4 factorial points, 1, 2, 3, 4 factorial points plus 4 axial points. So these are axial points like 1.4 because this is a 2-factor and its value will be 1.4. So there are 4 factorial points, 1, 2, 3, 4, and with 5 center points, 1, 2, 3, 4, 5. Total will be 13 for this central composite design with this 2-factor. And this is the coded values and this is the actual values. So these are the properties of central composite design. Now, central composite designs can be run sequentially. The first subset estimates the linear and 2-factor interaction, and the second subset estimates the curvature effects. The second subset need not to be run when the analysis of data from the first subset indicates the absence of significant curves. Means in the first points, from the factorial points, we see that there are no any significant factors or there is absence of significant curvature or significant factors. There is no necessity to run for this second subset. Directly change your current operating condition and start for your second experiments. Central composite designs are very efficient in providing information, experimental variable effects, and overall experimental error, and minimizing the number of runs required. The availability of several varieties of central composite design enables the use under different experimental region of interest and region of the operability. Means the range for central composite design it works on. So this was about central composite design. Now, what are Box-Behnken designs? So Box-Behnken design, these are also from this response surface designs, a type where designs on the response surface methodology with 3-level factorial designs. The set of experimental design for response surface methodology has points at center and midpoint at each side. It is used for fitting the response surface and used to estimate the second-order polynomial equation. Now, what does this mean? Like central composite design, we have 4 different blocks: block 1, block 2, block 3, where each factor is given a range of levels: 0 for x3, 0 for x2, 0 for x1, and this is the center point, which has its midpoint like 0. So these are different axes for x, a, b, and c factors. These are different treatments for Box-Behnken design, and this Box-Behnken design does not contain any surrounded or factorial design like that was in case with central composite design. It is used in addressing the issue of where experimental boundaries should be In particularly, to avoid the treatment combinations at extreme, means the design, it should work within the design space. It should not go near to the limits or the edges of the design space. The Box-Behnken design avoids all the corner points and star points and extreme points. The treatment combinations are at the midpoint of edge of the process space and at the center, but they are not at the star points or axial points, which are the extreme points. So Box-Behnken designs, those are rotatable, require 3 levels, coded with -1, 0, +1, available from 3 to 10 factors. In this design, 3 factors were evaluated at 3 levels, and experimental design was carried out for a different possible combinations. So this is a tabular form which states us that when we use 2 factors, how much runs will this Box-Behnken design and central composite design will give. If I'm using 2 factors, yes, Box-Behnken design can't be carried out because it starts with 3 factors till 10 factors and above, and central composite design, it starts from 2 factors to the above. So you can see here for 3 factors, 4 factors, 5 factors, the number of experiments for Box-Behnken design and central composite design. So these are different number of runs. Those are required in a tabular format for central composite design and Box-Behnken design. So the softwares that are used for this response surface methodologies or design of experiment, these are SysStat, JMP, MATLAB, StatGraphics, R, Design Expert, Minitab with the recent versions. These are just the logos, but the recent versions will give you more specified properties or the factors or the levels which you can use into the graphical format. So this was about the response surface methodology, its steps in experimentation, objectives, and now give me just this few minutes so that I can just show you the screenshot when we are using a tutorial for Minitab by using the central composite design and Box-Behnken design. So here the Minitab version 19 was used, and those were different experiments with X1, X2, and this was Y, this was response, this was standard order, and central composite design with help of Minitab was determined. So central composite design, go into stat, DOE, response surface, create a response design, where you will go and you have to specify a design. It will tell you central composite design or Box-Behnken design. Here we are starting with the central composite design. It will tell you how much factors, note the factors, 2 factors, 3 factors, and you will get a design. Specify the number of factors, options, how much options, how much categoric factors, and which randomized runs, replication runs need to be performed. Specify the results, in which type you want the results, summary table or summary table along with the design table. Specify those and press OK. You will get the different, you will get a result in a different screen, and that screen will be with these 2 factors A and B. Once you get this levels designed from the software, run for it, specify the factors, identify the response, and the response was Y was the confront, and this was the response which were identified, which was run after running this treatment trials. And when I have the response, I will start to analyze my response surface plot. It is stat, DOE, response surface, and define custom response surface design. When I go into this, I have to select my continuous factor against which I have to determine my response. So continuous factors were selected based on the central composite design, axial points, the factors had given the values, and the response was selected. There were no any categorical factors, and analysis was done. Analysis is the step where you go into stat, DOE, response surface, and analysis of response surface design. And this you click on analyze, and once you get analyze, select the response, that is Y, and then press OK. Then you will get a full quadratic model, because this response surface plots are of full quadratic model. And if you get this, select for the options which type of randomized form you want, or with how much confidence interval you want, select it and go step by step. It will select the main effects, individual interaction, and the interaction between the 2 factors. Then press OK. Select the type of results display you want. You want a method, analysis of variance, model summary, coefficient, regression equation, and fits and diagnostic. Press OK. Then you will get the result in form of a sheet, which will tell us the coded coefficient and the ANOVA. Now, the important thing here in this Minitab is the p-values and the coefficient along with the R-square. So these are the important factors which you need to see to predict the response for the selected response at a different dosage form as per your trial. So the R-square, these are the factor modeling, and that response should be above 80. It is said that it should be above 80. Then we say that the model is a significant model, or the model is within the investigation, or the no anymore investigation is needed. Also, along with these p-values, coefficient values, and this R-square, there are different graphs which needs to be considered. This graph tells us the Pareto chart for interaction terms, individual terms, and individual interaction terms, along with this regression equation. So this equation tells us the equation for individual factor, reaction temperature, humidity, reaction temperature, individual interaction of humidity, and two different factor interactions. So this values will be more important when you select the curvature term, because this is a response surface methodology, and response surface methodology, when there is a curve, the factor should be taken into consideration. Look at the impacting factor which are more impacting, and the curvating factor which is called as the quadratic terms. And then go for the counterplots, stats, DOE, response surface, counterplots, and you will get a counterplot. So as we have discussed previously, that once you get these counterplots are the lines, those are joining the points of equal elevation of a surface. So this will have one value, this will have one value, but those each and every line will have a specified value. Now, when you consider this graph will tell us the dark region ranges gives us the comfort region. This ranges from 65, so from here till this 75 till 75. So this is my region of optimum and not the current operating condition, and this will give me a desired result with significant values. So here this color indicates the higher impact, higher values, reduced levels. These are the counter intervals what we have discussed, and maximizing the response, because my response was maximizing. And these values, if you see here, 2.5, 5, 7.5, 7.5, those are increasing because I had set my experiment to the maximization form. So this is about the counter plot. Then we go on to the response surface plot, same pattern, stat, DOE, response surface plot, and I plot a response surface plot including all these quadratic terms and the curvature terms, and I get this form. So this response surface plot, if I plot this with the counter plot below this, there was a center circular form in the counter plot, and that was my maximized region. And so if you go back and just recall the types of response surface plot, from this type or shapes of response surface plot, this shape is of maximize, where the center part is maximized. And so if you see the shadow of this in form of counter plots, the counter plot is circular in the center, because this part with respect to response surface plot is maximized, and the shadow will tell me my exact region of optimum. So here you can see two different factors with the scale with response surface plot. The factor goes on increasing, and this is a 3 plot with maximum confirmation showing me that this is my area of optimum, or I have performed the experiment in the design space. If it would have been a ridge type or a saddle type, I need to have been investigate further to define what type of interaction or what type of graph I would get it. So this was about the center composite design, and the last part is creation of a Box-Behnken design. This part is similar to that what we have did for central composite design, and here this was the experiment which we had done. This is our paper which has 3 different factors for particle size, and same pattern was followed: stat, DOE, selection of a Box-Behnken design, selection of a design from the terms, naming the factors, naming the units, then selection of a randomized term, selecting the summary table and the design table, clicking OK, having a screen design for the different runs, performing the runs, having the responses for particle size, and analyzing them. So analysis was done like DOE, response surface, defining the response surface, and analyze. Analysis was done with selecting the continuous factors against the response factors. The factors were then mentioned for the low value, high value initially itself. If those were coded, their values were given and the actual values were given. Then analysis was done, selection of the responses against the responses of against the input variables or controllable variables, selection of the full quadratic term, and plotted and predicted. So here also the same factors are responsible, like p-value, r-square, and coefficients. So this will tell us whether the p-value is there. So we can see here that amount of gelatin gum has a significant value than the other factors present in this design. So that will be my impacting factor. This is analysis of variance. This is the regression equation. This is not a screening design, but this is a Pareto chart which will tell me what are the impacting factor for increasing in the particle size. So A is nothing but amount of gelatin gum. The gelatin gum is responsible for increasing particle size, but this will not be dealing with, because as this is a response surface plot, not a screening design, we will go for response surface design and a counter plot. Now, when you see this response surface plot and this counter plot, this is similar to the linear approach, linear or the first order model, but has slight or little presence of curvature, which is designed or depicted in this counter plot. Now you can see here, this was a maximization, increase in the response, increase in the response, increase in the minimum, increasing in the darker color, and shows the region of interest or region of the optimum region. So I need to have performed this practically here. This counter plots and response surface design tells me. So for particular factors, now these are the other number of factors which tells me the similar little curvature design with respect to the response surface design. And the third factor tells me a ridge or a saddle type plot where it says that it is slanting towards one end and shows me a curvature plot in the curvature design in a counter plots, which has some joining lines with some specific values, difference in the color shades, which is representing the response surface plot, its shadow. So this is about the Box-Behnken design with respect to Minitab, and here my presentation ends. So if you have any doubts, if you have any queries, you can ask. So this is with respect to Box-Behnken design, central composite design, Minitabs, steps into design, steps in design, and its objectives. So over to you, Dama sir.
Okay.
Yes, sir. Thank you, Ashwin, sir. Thank you. Thank you very much. And actually, it was a very informative session that you have been covered, and full of details regarding the everything and the software that has been. First, Apollo, we'll have them some question answer session, and then.
Yes,
talk.
sir. Yeah. Yes, sir. Yes.
Mantri sir.
Yeah. Yes, sir.
Mantri sir is there?
Yes, sir. Yes, sir.
If some few participants having the questions, they can raise their hands.
Yeah.
Already they have raised.
First participant.
Kamal Singh Rathod sir is there. Who wants
First,
to ask the question.
Dr. Kamal Singh Rathod.
Yes, sir. Good evening.
Good evening, sir.
Good evening. It's a really, really very informative session, Ashwin sir.
Yeah, thank you, sir.
Really, previously I was also thinking that I have to join this design of experiment session somewhere, and Mantri sir invited. Thank you so much, and I find it really informative. And my pet read regarding this topic was now less, and my region of interest increases. Region of operability also, I think, increases. And I have small queries regarding this,
Yes,
that how we can use in our day-to-day experiment in laboratory. I think it's really useful there also. So
Yes,
is there any site or any book which is useful for in this case, or any app which is available for we can use on small scale experiments of because the Minitab, and this is, I think, the costly, we cannot everyone cannot have all these things.
Yes, sir. I can tell you with respect to the thing. Thank you, sir, for appreciating this. And the book which is there, it is Design of Experiment and Analysis, which is by Montgomery, Montgomery. This is the book which is there in by Deck series. You can refer this book, and all the contents, mostly all the content was covered from that book. And
Right.
there is no such app, but I can suggest that there are different sites where you can see or select different mechanisms or the process which you want to learn from the lab scale, or else you can visit to the different sites like Minitabs, Design Expert, where there are case studies, and those case studies will help you to design from the lab scale for the
Right.
scale-ups.
Thank you so
Right.
much.
Thank you, sir. Thank you.
Thank you, sir. Next participant name is Junyat sir. Muhammad Junyat. Okay, we'll move to the next participant. Dr. Satyabrata Bhanjo from Hyderabad.
Hello.
Hello.
Yes.
Hello, sir. Good evening, sir.
Good evening, sir.
Actually, it is a very nice session, sir. I appreciate it, sir. And also, I thank to Dr. Dama, sir, is the principal, and also Dr. Mantri, the organizing secretary, and also their team. They are conducting such a beautiful session or the webinar. Thanks to them, sir. My small doubt is there.
Yes,
So,
sir.
suppose you are going for any new formulation.
Yes, sir.
Suppose there is no methodologies available. So how
Okay.
can you put the control and uncontrolled factors? How to select?
Yes, sir. So first of all, you should know which type of dosage form you are going to design, or
Okay.
what type of experiment it is, or what are the targets for your experiment.
That's it.
Once you know what are the targets, you will know what will be the inputs to achieve your outputs, right? So once you know what are the inputs, for example, if your experiment is with respect to, consider now a tablet dosage form, it's a conventional tablet dosage form. So your target is a tablet dosage form. Your inputs are API. If the dose you don't know, you need to screen it. If the excipients which are to be selected to develop a tablet dosage forms, if those excipients are not been selected, first I suggest you to screen those excipients with respect to your tablet dosage form. You will get few out of the vast number of excipients you have selected. Then select only those selected excipients from the screening design, because the selected excipients from the screening design will be the excipients which will be showing you the main impact or highly significant factors or highly significant excipients on your tablet selected response. Then it will be easy for you to select 2 excipients or 3 excipients from 10 excipients. So you will get an input variables. And once you have less number of input variables, and you know that you have to prepare a conventional dosage form, depending on the nature of the API, depending upon the nature of the excipients which you are using, you can design, either you can go for a wet granulation method, either you can use an aqueous solution, either you can use an non-aqueous solution like organic solvents, or you can go for direct compression if your excipients and API properties are good, or else you can go for the roller compaction. So based on that, the process will be defined. You have defined your excipients, and then you can formulate a dosage form, and that will be a screening design along with a response surface designs.
Sir, whether sir dissolution factor will be impacted?
Yes, you can select. Yes, they can be impacted. Either you can select a dissolution factor like factors that will be responsible for 2 hours, 25 hours, 40 hours, 45 hours, 75 hours, depending on your nature of tablet. If it is sustained release, if it is conventional release, if it is immediate release, depending on that, you can select the dissolution factor, and definitely it will impact on the dissolution factors, and basis on the nature of the excipient you select, and basis on the API, whether it is highly soluble, insoluble, and all.
Okay. Okay, sir. Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you
Bhanjo,
also,
sir.
organizer. Nice.
Next, we're coming to the next participant, Dr. Manas Kumar Katwal from Punjab. Yes, sir, you can
Hello.
ask your question.
Sir, am I audible?
Yes, sir. Yes, sir. Tell me.
Yes, sir.
Okay.
Yes,
Good
you are
afternoon,
audible.
sir.
You can ask your question.
Okay. Sir, first of all, thank you so much for such a wonderful session. and I feel myself privileged to be the part of this webinar. Sir, my question is there any particular software to calculate the KADME of any of API? Any software available for calculate the KADME?
Sorry, sir, I don't
the
have any.
pharmacokinetics values of any
Yes,
new API.
it is related to pharmacokinetics. Actually, I don't have any idea. If I find out, I will definitely tell you, because this is more relevant to the ADME part, and this is related to the statistical or the response surface methodology or optimization part.
Okay, sir. Thank you so much, sir.
Thank you, sir.
Okay. Thank you, Manoj sir. Next participant, Prabhu. Okay, we'll move to the next participant. Name is Amal Golab. Amal ji, can you hear my voice?
Yes. Am I audible, sir?
Yeah. Yes.
Hello, sir. Ashwin, sir.
Hello. Hi.
Sir. Actually, I'm actually working on QBD
Yes,
with the design expert. So actually, I have faced one problem.
yes.
So
Sir.
when you do the literature survey, particularly when you're working with the phytomedicine and nanotechnology,
Yes, sir.
some researchers has given a stress or emphasis on formulation factor,
Right.
and some has a focus more on the process factor.
Right.
And when you compile both of these factor, it is a quite a huge bunch of factors.
Huge one. Right. Sir.
And actually in academic, we know that we receive only a little bit quantity of the sample of the phytoconstituent. And for a better interpretation, we
Right.
require to run so many
Right.
trials. So in that case,
Right.
how we should proceed? Means which type of factor we should prefer? Formulation or process factor?
First of all, we should know that which is the main governing factor or main governing parameters. Are they formulation oriented or a process oriented? I will suggest first decide whether the process is impacting more onto your product, means onto your formulation, or are the formulation variables impacting more. When you come to know this process of formulation, go detail into that. Select the process which are the process parameter. Like if you're developing, if you're with a one process which has a stirring time, which has a temperature, which has some amplitude, which has some homogenization speed, different types of parameters from the process. If the process is getting impacted, select those, select the most impacting parameters from them, and perform the design, perform the experimentation. Because performing or considering all the factors from process or considering all the factors from formulation will not be much easy into this consideration in your current situation, because we will not be getting or we will not be identifying which is the majorly impacting factor. So first identify which is the major governing factor, and from that select the design basis on the number of factors. And I suggest to select a design which will give you more robust results with less number of runs by using your defined number of factors.
Okay. And sir, can I ask a second question?
Yes, sir. Yes.
Yeah, sure.
Actually, sir, second question is, sir, suppose we need to interpret the control plots.
Yes.
So is there any requirement that we should know some basic knowledge of statistics? And if somebody wants to learn the interpret the control plots from the scratch, how one should start with?
First of all, I will like to tell that yes, definitely statistics is there. Statistics is what is DOE is, because DOE is full of statistics. Second part, to learn these counter plots, first we should know what exactly the lines which are there in the iso response part in the counter plots, what the color, dark color to faint color to dark color indicates, and how is it impacting your response. And this you will get more information on this website itself, which tells us more about the softwares.
Okay, sir. Thank you, sir.
Okay. Thank you.
Thank you, Amal. Next participant, Rajesh Kumar.
Hello, sir.
Hello.
Yes, sir. Good evening.
Good evening, sir.
Good evening, sir.
Yes, I can hear you, sir. Yes, please, Rajesh, sir.
Yes, sir. Thank you.
Yes,
Yes,
Rajesh.
Rajesh, sir.
Factorial design, sir. Factorial design, 2 square.
Hmm.
Hello.
Hello.
Sir, what is the maximum number of variables I can put, sir? Dependent variables in 2 square factorial design. How many maximum variables, response variables I can include in my formula?
See, response variable
2
there
square, sir.
for 2 square there is, for any factorial design there is no any such limit that you should have one response or two response or three response, or there should be
Yes,
a
sir.
number of response. First of all,
Yes, sir.
for identifying what is output, if you are having 5 responses,
Yes, sir. Yes, sir.
identify which will be the
Yes, sir.
most important response. If I say that I'm preparing a tablet, and if I consider thickness, hardness, weight variation as my response,
Yes, sir. Yes, sir.
and if I say that drug release is also their response, but if my tablet is a sustained release tablet, and if I say that it's an enteric coating tablet,
Yes, sir. Yes.
and I want to identify or I want to determine or predict the amount of
Yes.
drug release after 2 hours where the coat will be dissolved, and I
Oh,
want to
yeah,
also
yeah.
I want to identify or predict the result
Yeah.
release after T50 and T75,
Yes, sir.
then I will focus only on the drug release,
Yes, sir.
because when this type of
Yes.
dosage form is there, then this post compression or pre
Yes, sir.
compression parameters will not be that much important.
Yes, sir. Yes, sir. Exactly, sir. Yes, sir.
Right, right.
Thank you, sir. Thank you, sir.
Thank you.
And one more
Thank
thing,
you,
sir.
sir.
Thank you.
Actually,
Yes,
it is
sir.
a vast topic, and I congratulate Ashwini Kuchekar, sir, for his elaborated and patience explanation of 103 slides. Once again, I congratulate you, sir.
Thank you, sir. Thank you. Thank you, sir.
Thank you. Thank you, Rajesh Kumar, sir. Sir, we will move to the next participant. Name is Om.
Okay. Hello.
Hello.
Yes.
Hello, Ashwini sir.
Hello. Hi. Hi, Om.
Uh, Sir, actually, a very fabulous lecture. And I am
Thank you,
first
sir.
of all congratulate Dr. Dama sir and his all team members. My question is related with the axial point where we can jump with the different type of points together. That means 1.414 or
Yes.
1.682 even.
Yes.
So
Yes.
when we are supposed to get these coded factors, no, then that time how one can convert that coded into the actual values.
See,
So
this
what kind of part you will going to take? I
yes,
mean value.
value. Yes, I'll tell you. So first of all, this axial values or the star points in coded values, we have to select based on the number of factors and number of trials, means number of runs for different central composite designs, right? If it is spherical, it will be by number of factors. If it is by circumscribed and inscribed, it will be for the number of trials. So once you know what is the number of factor, we will consider this example as number of factors depending on the K. If it is 2, number of factors are 2. We know that that value
Okay.
we will get is 1.4 because its formula is number of factors raised to 1 upon 2. This will be our coded terms. Now, when you input your actual values for x1 and x2, if it is a 2 factorial central composite design or a 3 factorial central composite design, that values software will identify this axial or the central values itself and send us the axial values with respect to 1.4 for 2 factors. For 3 factors,
Okay.
that software will give you a 3 factor axial value. It will be 1.6 or 1.7 for the 3 factors, and that values will be
Okay.
based on the low level and high level what you have selected.
But
Because
actually, sir, I am. Yes. Sorry.
because that axial value is the distance from the center and the low and high level. So that distance
Yeah.
is calculated by this low value, high value, and the center points.
Okay. But actually, sir, last from 2 to 3 years, I'm trying to just correlate this data with respect to this axial point, but I couldn't get that data properly because I have asked that Chandramouli sir in the apti sessions
Yes.
too, but I think so he was quite of fed up of number of questions being asked. So that's
Okay.
why I was not happy with that answers what he said that time. So that's why
Okay.
I'm. I think so. You were also joined to that meet.
Yeah, I was also there for that. Yeah, but according to me, this axial points are the distance. Is the axial point is the distance from the low and high points or high level and also from the central level, because these are the star points, and so those are placed into the axially points.
So software automatically giving you
Yes.
that point.
Yes. In Minitab itself, when you
Okay.
go, you will get the values.
Okay.
So hope
Okay.
you are
Because stat is I'm using for, so that's why I'm not getting that value.
because in
It's maybe due to the
in center composite design, when I showed you the Minitab screenshots, there you will find out that there was one point or one slide or one screenshot which tells us that when you input the actually low values and high values, you are getting the axial point values there.
yes. I got that
Yes.
screenshot even.
Yes.
Okay. Thank you, sir. Thank you, Ashwini
Thank you.
sir.
Hope you are happy with this
It's my
answer.
humble request to Dama sir. Yes.
Yes, sir.
It's my request to Dama sir as well that please, if possible, then you can please send that PowerPoint presentation of Ashwin sir too. It will be quite helpful
Sure.
to we as a budding faculty member in that field.
Actually,
Okay. Thank
we
you,
have
sir.
the live session of YouTube also, sir. You can everything is
Yeah.
live today. It is also there. Then also Ashwin sir will
Yeah.
share you. Don't worry.
Yes,
Sir.
definitely I'll share you. Yes, I'll share you.
Ashwin sir is my good friend, sir. No problem.
Okay. Thank you. Yeah.
Okay, sir. Okay.
Thank you.
Thank you, Om sir. Nitin sir, sorry. Ashwini sir, so here we want to close the session, questionnaire session.
Yes.
So because some of the participant still also they're raising their hand, but we have to complete the session during the time only. So before coming to the next, I request to principal sir to take the in charge and say about the today's sessions.
I'm very thankful, Ashwin sir. Very much thankful for
Thank
your
you,
this
sir.
today's session, because it was a very informative and exhaustive, informative session. It is one
Yes.
of the fabulous session.
Yes.
Because the depth of knowledge that that you are having and you have shared with all the participants today, and I think that it is not a topic of the one day that one can get it understood. And I
Yes,
think
sir,
it will
definitely,
take if one has to get it the finished product, I think that he has to work on this, on your slides, whatever it may be. He has to go
Yes,
through that
yes.
slides, and then he will be possible to work out to get the finished product and all that. And I'm thankful to you, sir. Really, I'm
Thank
very
you.
thankful for you, for on behalf of our team also, and on behalf of our staff members also. And
Thank you
I'm
very
very
much,
much
sir.
thankful to Kuchekar sir also, because he's my overall he's my guru actually, and I'm thankful for Kuchekar sir also, because even in the session what you have been covered numbers of the things, means just little bit whatever I have been noted down. We have regarding that to the design of the experiment that is being needed, what the staff or what the PG students or what the PG guide student they should be work, that they should work on the design of the experiments, and then they go for the what they are going to obtain the finished products and all that. Even the formulation and the product design you have been discussed. Number of things you have discussed a very in a diagrammatically the input, process, output, and finished product. You have explained very nicely, sir.
Thank
Because
you very much, sir.
they are step by step, even by point to point, you have been noted that so that a small kid can also understood that process, how one has to be get it to catch up the process and all that for the finished products. And even you have highlighted regarding the factorial point that has to be selected during the experimental design and all that one. Even the steps of the experiment that you have been covered, the experimental object that has to be noted down first of all, so that it should be planned out. The experimental design and the objectives, according to that, you should be get it planned out first of all. And what are the controllable and uncontrollable factors that has to be keeping in mind, you have to get it the design that of the experiment. That is the most important that you have been highlighted over there. Even the steps in experiments, what has to be taken, even the general readable reports has to be, what reports are to be expected from your
Yes, sir.
experiment, that
Yes,
has
sir.
to be get it planned earlier. That are
Right,
also
sir.
you have been highlighted. Even the randomization of the clear concept of randomization,
Yes, sir.
how it should be plan out, or how it should be get it selected. That has also been, even you have been highlighted regarding the replication and repetition. What is
Right.
replication, repetition?
Yes,
that you have been also very covered in a very simple way. And even the RSM optimization, in that RSM objectives, you have been covered optimization. What should be the minimum and what should be the maximum? That
right,
you
sir.
have to decide it, and
Decide.
then only you can go for that one. Even RSM process also, you have been work that work should be optimized and up to the desired values, whatever being to be covered. And overall, you have been shown regarding that of the uh, how the software it should be utilized and how it should be comfortable to even the micro and minutes or nano things that you have been highlighted through through your slides.
Yes,
And I
thank you,
think
sir.
that
Thank you.
this webinar might, whatever the participant there are, they might be fruitful from this today's webinar, because the chat, it was very fabulous for the comments for you in this
Thank you,
today's
sir.
chat. I will
Thank you,
share
sir.
you the chat also. And once again, on behalf of my college and Sri Chandra Pawar College of Pharmacy, I'm very much thankful on behalf of management, staffs, and all that. And
Yes.
thankful, Ashwin, thankful.
Thank you.
And
Thank
thank
you,
you, the
sir.
participants to be with you. Yes, sir. Thank you.
Thank you. Thank you, sir.
And
Thank
Ashwin,
you.
convey my regards to Kuchekar sir also.
Yes,
Very much
definitely, sir. Definitely. And if any
Yes.
of the participant has any problem, sir, my mobile number and my mail ID is there, so anyone can have a
It is there.
discussion.
It is there on the screen. They will be
Yes,
free to talk with you.
yes,
Surely.
definitely, sir. Definitely. Yes,
Yes.
sir.
Thank you.
Sir,
Thank
thank
you,
you.
all the
Thank you, sir.
participants.
Yes,
Thank you.
thank you.
Thank you.
Thank
Thank you.
you.
And
Thank you, Principal Sir. So many participants, they are giving the chart. What about the certificate and feedback? Dear participant, certificate and feedback form today will send to your WhatsApp group. So we are conducting 3 days continuously. Today is the 9th series, and tomorrow we are going to conduct the 10th series webinar, national level. The topic is metabolomic approaches for the development of newer biomarkers. That is tomorrow, 11 a.m. we are starting this 10th series, and also 11th series we are planning to conduct on June 5th, day after tomorrow. That topic is regulatory affairs and interesting and challenging profession. So this is the same time, 11 a.m. will conduct this. So tomorrow and day after tomorrow, 11 a.m. we're conducting the 10th series and 11th series. And don't worry for the feedback and don't worry for the certificate. Definitely will give the good service to all the participants. That is our responsibility. Because as you know, we have conducted 8 series webinar, and we have given the certificate within 24 hours to all the participants. That is all credit goes to our team members. Our team members, they are doing day night only for you, for making the certificate and all the works. Our responsibility to give the good service to all the one. Now I would like to request Dr. Sumit Ashok Joshi to conclude this session with your vote of thanks. Dr. Sumit Joshi, over to you.
yes, Sumit Joshi sir.
Hello.
Hello. Yes.
Are you audible? Yes, yes. Right.
Yes.
Okay.
Hello, everyone. Beloved Principal, sir. Our today's young and energetic speaker, Dr. Ashwin Kuchekar, sir. Ladies and gentlemen, it's my privilege to have been asked to propose vote of thanks for our today's webinar. I, on behalf of Sri Gajanan Maharaj Shikshan Prasarak Mandal, Sharat Chandra Pawar College of Pharmacy, Otur, management, beloved Principal, sir, organizing team, staff member, and my own behalf, extend a very hearty vote of thanks to our today's speaker, Dr. Ashwin Kuchekar, sir. Sir, thank you for sharing your views on response surface methodology with us. I will assure you that your today's lecture is a feast for PG student, PhD scholar, and all the faculty member, those who are attended through Zoom as well as through the YouTube. Definitely, it's a feast for us. Thank you, sir, for your wonderful and informative lecture. I would like to express my thanks to our beloved principal, sir. We have been fortunate enough to be assisted by our principal, sir. Sir, you have been a constant support and you have given us a lot of encouragement to conduct such type of webinar series throughout this lockdown period. So thank you, our beloved principal, Dr. Jiwai Dama, sir. And last, I would like to express my thanks to all the participants to conduct our today's webinar and at a huge success. Thank you one and all, and thank you our today's speaker. Thank you, sir. Principal,
Thank
sir,
you.
shall I conclude with your permission?
Yes, sir. Yes,
Yes.
yes,
Yeah.
yes, yes, yes.
Thank you, sir.
Ashwin,
Thank
sir,
you.
once again,
Yes.
thank you for you.
Thank you,
I'm
sir.
very much thankful for you, sir.
Thank you, sir. Thank you.
Yes. Okay.
Thank you, sir.
Okay. Okay. Thank you very much.
Thank you.
Dear participant, we are going to end this meeting now. We'll conclude this meeting. Okay. Thank you.